Welcome back to Chem 4300. In this video, we're going to continue Chapter 17 on the quantum mechanics of rotational motion. And what we're going to start now is looking at the solutions to the Schrodinger equation for the rotational motion of rigid molecules in each of these 5 different classifications. And if you remember from Chapter 4, these classifications are based on the principal components of the moment of inertia tensor. So, for example, the spherical molecule has all 3 components equal to each other. The symmetric molecules have only 2 components equal to each other, and those are separated into the prolate and oblate depending upon whether the 2 components, in this case B and C, are greater than the other component, A, or the oblate case where A and B, which are equal to each other, are smaller than the other component, C. And in these cases, we're going to assign the parallel component to the unique one, which is A in the prolate case and C in the oblate case, and the perpendicular component we'd assign to the 2 that are equal to each other. So B and C in prolate and A and B in oblate. Now similarly, asymmetric molecules are defined by their principal components as ones where A, B, and C are not equal to each other. And then we have the special case of linear molecule where one component, A, is 0 and the other 2 components are equal to each other. And again, molecules that have 2 or more threefold or higher symmetry axes are going to be in the spherical classification. Molecules that have 1 threefold or higher symmetry axis are in the symmetric classification. So let's start by looking at the solutions for the spherically symmetric molecules. So I just pulled up this little graphic here to remind you of a couple shapes that are spherically symmetric. Now, we start out with our Hamiltonian as before, but now in this spherically symmetric case, we know that A, B, and C are equal to each other, so we can assign just one constant. And you can see that when we set all of these equal to the same constant, this expression simplifies down to this expression. But then we recognize JA squared plus JB squared plus JC squared is just equal to the total angular momentum vector quantity squared. So that's just this operator. So it comes down to the Hamiltonian being this very simple form right here. And of course, when you put it into the Schrodinger equation, H psi equals E psi, then we get this simple expression right here for the differential equation. Remember, we had that expression here for J in the last lecture that we would solve for getting the eigenvalues and eigenstates. Now, we already know the eigenvalues. We know that the eigenvalues of J is just J times J plus 1 times H bar squared, where this is the quantum number, and it goes from 0, 1, 2, and so on. So we know then that the rotational energy, given this expression here, we can get the rotational energy that is just going to be J times J plus 1 times H bar squared over 2I. And so the energies are indexed by the rotational quantum number J. And so in terms of those constants that we defined earlier, the rotational constants, this is the wave number rotational constant B, then we write it this way for the energy levels. So, okay, I just said that. It's the wave number rotational constant. And so that is this I, and the rest of these are just constants. So one thing you may notice here is that there is no 0-point energy. So the lowest energy state, J equals 0, evaluates to an EJ, or E of 0 is equal to 0. So remember in the harmonic oscillator problem, we saw that the ground state had a 0-point energy, but in this case, we do not. And remember that this is free rotation. So just like free translation, there was no 0-point energy. And for free rotation, there's no potential energy surface that this molecule is rotating on. It's completely free, and for that reason, there's no 0-point energy. Now, the solutions to the Schrodinger equation for the eigenstates is not trivial, so I'm not going to try to work that out. I'm just going to give you the solutions. And the solutions have this form here, where we have our wave function now in terms of the Euler angles, and now we have our quantum numbers, J m sub j and k sub j. Remember, we have the angular momentum component along in the space fixed frame and in the body fixed frame. So we have these two quantum numbers here, and it's related to this function here, which is tabulated in many books. It's what's called the Wigner D function, and it has this form here where you have these Euler exponentiation, these Euler expressions here for phi and chi, and then this term here is something called a reduced Wigner D function. And again, I'm not going to get into the details, but you can look them up in any book on angular momentum theory. But the key thing is that we have these quantum numbers here that describe this wave function. J is the total rotational angular momentum quantum number, and then we have the components for the body fixed frame and the space fixed frame. So again, Kj is the quantum number for rotation about C in the principal axis system, and it's the projection of J onto the C axis. Mj is the quantum number for rotation about Z in the space fixed frame. So Mj times h bar is the projection of J onto the Z axis in the space fixed frame. Okay. Notice that the energy expression that we got in the previous slide is independent of K and M. So this expression here depends only on J for the spherically symmetric rotor or molecule, and so we have no dependence on K and J. So there's going to be a degeneracy. All of these states are going to have exactly the same energy, and we'll come back to this here shortly. So here's what that energy level spacing looks like. So if I'm going to write it in this form, it's really common actually to divide the energy by these constants, Planck's constant and the speed of light, to create this variable here, which is in wave numbers. And that's going to be given by the B constant, the wave number rotational constant, times J and J plus 1. And this is what the energy level spacing looks like for different J's. Here's J equals 0, J equals 1, 2, 3, and 4, and so on. And over here, I've written down the degeneracy for each of these levels. So in the J equals 0 case, well, we can only have values of Mj of 0 and Kj of 0. So there's only one state with these quantum numbers here with this energy level. And then for J equals 1, well, of course, we can have M sub J equals minus 1, 0, and plus 1, and K sub J of minus 1, 0, and plus 1. So that ends up giving us a degeneracy of 9. So what we get is 2J plus 1 times 2J plus 1 for these different states. Okay, so you have to multiply them together. You can see similarly then for J equals 2, where the degeneracy is 25. That's because we have M sub J from minus 2 to plus 2, Kj going from minus 2 to plus 2. Multiply those together, and you get a degeneracy of 25. Okay. Now, the spacing between these energy levels we can evaluate from this expression here, and you can see that plugging that expression in down here, we get that the spacing increases with increasing J. So it goes by as 2 times the rotation constant times J plus 1. So you can see it's 2b, 4b, 6b, 8b as we increase the rotational quantum number. All right, I'm going to stop for this video, and in the next video we'll look at the solutions for the symmetric molecule.